My name is Harry van den Akker. I'm Bernal Professor of Fluid Mechanics at the University of Limerick. And I'm going to talk about flows today because I'm fascinated by flows. Flows of fluids, any fluid, whether it's a liquid, water or air, I'm fascinated by it. The first thing to show is the River Shannon in Limerick. You will see how turbulent the flow is, in particular behind the pillars of the bridge. And the word turbulence, you know that when you are flying, because then the captain says we will experience a turbulence and you should buckle up, for then you will feel the vibrations in the airplane, and that's because of the air currents that around the airplane. Another example that's more fascinating and even more powerful is the waterfalls of Iguazu, the border of Argentina and Brazil and Paraguay. It's massive amounts of water that are pouring down the waterfall, and it's a roaring sound that you hear with that. On the other hand, you also know about the weather forecast. Every night you may look at the weather forecast and you see these maps of Europe with the high pressure zones and the low pressure zones and all the air currents that are a result of that. So you're very familiar with that. And a very nice example of the power of wind is a few years ago in Limerick when a storm was there at the River Shannon at the boathouse when the storm lifted the roof and then blew it off. It's very powerful. Another nice example also with airflows is with airplanes. You see these trails of these white trails in the upper air, sometimes with airplanes, and they are the result of condensation. They have nothing to do with the exhaust gases from the engines, and you can marvelously see this in this movie. So that's a very important aspect, the fascination by these fluids. But not only water or air are important, you can also think about volcanoes. That's very different material. It's magma, very hot magma from the inside of the earth. It's coming to the surface of the earth, and then you see how turbulent this flow again is, with eruptions of gas, so that is an additional difficulty, and also the heat aspect is of course very difficult, and not only within the crater, but also when it has left the crater and flows into the environment, then you see how difficult and also magnificent these flows of liquid magma are. So, but it's not only about fascination by by these flows. I really like to understand flows. What is driving them? How do they respond to external conditions? So I do experiments. I run computer codes. I develop computer codes just to be able to predict flows in equipment. That's a difference. It's rather similar to the weather predictions, but now it's in industrial equipment. My interest is in industrial equipment and flows within those equipment. Another example, not really industrial, but also that is familiar to you, that's the blood in your body. Sometimes it's dull flow because it's laminar flow, very gradual, slow flow. In that respect it is dull. But sometimes people suffer from plaque, fat deposits in the interior walls of the arteries. And when a certain piece of such a plaque is released by forces exerted by the flow, then the flow transported maybe into your head, in your brains, and causes brain damage. So that is the challenge, to understand how these little fragments are transported by the blood flow and to which arteries they really go. But turning back to industrial flows, I will give you a few examples of multi-phase flows, so solid particles or gas bubbles in a liquid carrier. The first example is about solid particles in a liquid. We call that hydraulic transport or transport of suspensions, and that's relevant in the mining industry, for instance. Think of sand, transporting sand or sand-like material through a pipeline. Then the question is, how much power should your pump have to transport liquid ends, including the sand, over a distance of a few kilometers, for instance. So we did computer simulations of a limited number of particles and how they react on shear. So shear is if between two flat plates, one plate moves to the right, the lower plate moves to the left, and then there is a velocity difference that acts on these particles. And we show in this movie how these particles move, how they rotate, how they collide, and how they behave as a mixture. That's important information that we need for making the prediction about the relation between pumping power and transport rate. If these solid particles are liquid, so then you talk about droplets, and if these droplets experience such a shear, they can break up. And that is shown in the following movie. It is about that liquid droplet that suffers from the shear. So it's protected by a surfactant, but that is not always enough, and sometimes it still breaks. Another example is of research I'm involved in at UL is the pneumatic transport of dairy powder particles. That's a mouthful, but your interest is in dairy plants, is to transport dairy powder particles from one part of the plant to another part of the plant. That goes with air through pipes. And these pipes, 10 centimeters in diameter, they have horizontal elements and they have vertical parts, and the particles have to be transported by blowing air. And the problem with dairy particles is that they are very sticky, so they can stick together, so that means that the size and also their weight increases, and that makes it more difficult to transport them. And they also can stick to the walls, even to the effect that the pipeline is plugged, and then the plant has to stop, or you have to hammer out the sticky material. So we are simulating that by means of a computer code. There is a test loop in UL, and we use that as an example. It has a horizontal part, it has a vertical part, it has again a horizontal part, and then a horizontal bend. So there are 3 bends in the system, and that's a difficulty for these power particles to take them. We show you in this movie how these particles travel around these bends, how they dance in the vertical part, how they collide on the walls, and how they stick to the walls. So that's a very important aspect for improving the performance of dairy plants. And then the last example is an experimental investigation. It's about bubbles in a liquid. We built a test rig about 5 meters high. The actual interesting part is 2.4 meters, it's in the figure, and there is where you see the bubbles and where the bubbles rise. They are formed at needles, hundreds of needles. They all are identical, so we know exactly the size of the bubbles formed from these needles. They're all the same. They rise with the same velocity, and you can show that in this movie where you see multiple nozzles with all these bubbles escaping from them, and they are more or less the same. In the beginning there are trains of bubbles, but a little bit higher you already see that they are redistributed in the horizontal plane. And then in the last movie you will see the overall behavior of the bubble column. In one part, the right hand part, the airflow rate is higher, there are more bubbles, so the bubble rise speed is higher, and that means that on the left hand side the bubbles are entrained by the right hand side, and you get even downflow in the left hand side, and we are measuring all types of aspects of this bubbly flow. So I hope that I shared my fascination about multi-phase flow in particular with you. And if you have any more questions, then you may contact me, Harry van den Akker at University of Limerick.